examiner. ZMB. One letter. CMB. Competition. I don't see a thing. Yeah. Oh, I should never parked over here because these fucking ugly ass doors. Don't think about it, be about it. Yeah. Yeah. And girl, you vibe, but if I tell you, then you might take it to the head. I'm in my zone. Then I got my eyes closed. One shot. Thank you, Queen. That Uber was lit, I'm telling you. That motherfucker was lit, honey. I'm so tall. Look, I'm almost to the... I'm a big bitch. I should have parked on the other side because that side is right through those doors over there. And I wouldn't have to walk all the way through this fucking dumbass garage. Then I gotta pee. What day? 12:18, okay. For the first 5 minutes, the bitch just be yapping. So I'll be okay. And girl, you vibe, but if I tell you, then you might take it to the head. All right, you guys, we made it to class. We're 3 minutes late, per usual. But I gotta pee, so I'm gonna first walk in class, drop my backpack off, and then go pee, and then hopefully she ain't. Oh, here, this is one of my classmates, I think, right here. He be sitting behind me. They be talking so damn much, and I be having my hearing aids in, so I be hearing their whole conversation. And finally, like at the end of the last class, the teacher was like, "Hey, why are you guys talking so much?" And I'm like, "This is not high school. Like, no, the teacher shouldn't have to tell you to shut the fuck up. Is you cool? Bitch, let's be here for education, boo. We grown ass people. You don't have to come. Dead ass." So, yeah, we getting it in. And girl, you are, what if I tell you you are? And girl, you are, what if I tell you you are? Yo, what's up, John? Yo, what's up, John? What do you say? Cal 3, that's one of my... Oh, that's one of my workers. School is almost over, yes. Last one. Okay, I'm gonna sneak y'all to my class. Shh, shh, shh. It's cool. It's cool. I'm gonna look to the Wi-Fi. I'm gonna look to the Wi-Fi for y'all. I'm gonna look to the Wi-Fi for y'all. I'm gonna look to the Wi-Fi.
This is your region. So counterclockwise, like that direction, is positively green. If I do the other direction, that would not be positively green. Oh. Okay, so this theorem says, if we have such a curve, a positively oriented, piecewise smooth, simple closed curve in the plane, normal curve, it's closed. And D is the region bounded by C, so like the region inside that closed thing. And P and Q have continuous partial derivatives on an open region containing D. Then we can take the contour integral or the line integral over C of P dx plus Q dy and rewrite it as the double integral over the interior region D of partial Q partial X minus partial P partial Y with respect to A. So this is letting us change a line integral into a double integral. And then just notation-wise, I want to remind you that if we have like a vector field that has component functions P and Q, then this line integral is the same as the line integral of that vector field dot dr. Like it's just different notation for the same thing. Okay, so all the line integral stuff, like right now we're using this notation because we're doing a lot of work with the two component functions, but it's the same as this stuff. Okay, just a couple notation things. If C is a positively oriented closed curve, we sometimes write the integral with a little circle in the middle, right? Like this little circle thing, that's just saying I'm doing a line integral on a positively oriented simple closed curve. Okay, it doesn't really mean anything if you leave it off. So if you just want to be lazy, just don't write it. Okay. I will say sometimes the textbook will give you a problem but not tell you which way C is oriented. Like just say C is the unit circle, right? But if they give the problem with that symbol, it means it is positively oriented. Thank you. Okay, and then if we have a region D, so thinking instead of starting with a curve C, starting with a region D, then we can use this notation, which is like the partial symbol, but we call it boundary in this context. So the boundary of D to indicate the positively oriented boundary curve of D. And then just using that symbol instead of C, Green's says that the double integral of this particular combination of derivatives is the same as the line integral over the boundary of D. Exactly the same as this, only using boundary D instead of C. Okay, so we are going to practice. Hold on, let me put these where they need to go. Okay. Number one, we're going to evaluate the line integral where C is the positively oriented triangle with vertices 1, 0, 0, 1, and negative 1, 0. Okay, so first thing I'm going to do is sketch the triangle we're talking about. Okay, so 1, 0, 0, 1, and negative 1, 0. Negative 1, 0 would be over here. Whoopsies. I didn't quite leave myself enough space to make that. And it's not terrible. Okay, and it's a triangle, so we know we're talking about this. Okay, because it's positively oriented, tell me on the x-axis, would my point be going to the left or to the right?
To the right.
Very good. To the right. Okay, so it's going this direction. Okay, now, I'm just going to throw this out here. We already know how to do this, right? We can parameterize this curve in 3 different pieces in terms of t, right? And then take the x in terms of t and the y in terms of t and plug them in here and take the derivative of the x part and put it there and the derivative of the y part and put it there and then just integrate with respect to t on the 3 separate pieces. Okay, so we could do that. Green's theorem is just giving us a different way of doing that. It's a lot easier. Okay. So, let's see. We could parameterize the 3 parts of C. That's all I'm going to say about that. We're not going to actually do that right now. Okay? Instead, I'm going to tell you that this part, the part in front of the dx, is what we usually call P, and this part, the part in front of the dy, is what we call Q. Okay? And by Green's theorem, this integral, the one that was typed, is equal to the double integral of partial q partial x minus partial p partial y with respect to a, where I'm integrating over d. I started writing the d in the wrong spot. Okay, and what is d? It's just this triangular region. Okay, so now if this is p, x to the 4th plus 2y, what is partial p partial y? Sorry, started pointing at the wrong one.
2.
So the derivative with respect to y is 2,
Oh,
because that doesn't happen. Okay, so weirdly I did the second term first, sorry about that. Okay,
Yeah,
so that one's 2. Well, because I wanted to do p first. Okay, now do this one, q partial x
5.
is 5.
Yes.
Okay,
So, how did you know exactly, is P always going to pertain to with respect to X in the integral?
p is always the one with the dx,
Okay,
and pretty much always it's the one written first.
okay.
But theoretically, we could switch it, it's just we don't know.
Would it be negative p plus q then?
Huh?
If we switched it, would it be negative p plus q? Or is it still?
No, I mean, we could write this as 5x plus sine y dy plus this dx.
Oh, it's just up there in the double integral, it's minus, so I don't know if that changed it. Or you switch it
So-
to this type first and then it's plus.
That wouldn't change it. Okay, and we know 5 minus 2 is 3, and that's a constant. I know. Okay, and now why am I not bothering to figure anything out about d? Because the only thing I'm integrating is 1. And if you integrate over a region, the number 1, you just get what?
Balance.
I think someone said it.
You get the variable.
No,
What
I'm
was the question?
integrating over a region. It's a definite integral. I get a number.
Mhm.
What number?
5.
0, 3.
1.
Okay, a double integral over a region D of the number 1, so this is the area of D. So rather than be fancy and find equations for that and antiderivatives and plug in, I just need the area of that triangle. Just,
Does that always happen with Green's theorem?
no.
Dang it.
Okay, so this is the area of D, 3 times the area of D. And let's see, that triangle has width 2 and height 1, so what's its area? 1. And 3 times 1 is 3, so my final answer is 3. So someone said it. Or someone said 3.
Someone said 3. Good job, someone. You did it.
Yeah, but that wasn't the question I asked.
Well, I did say 1.
Oh, okay, good.
Bro is someone.
Okay, now, you see how that calculation was easier than parametrizing 3 sections of the triangle and doing everything in terms of t and doing 3 integrals and then adding those 3 things
Mhm.
together?
Mm-hmm.
Okay. What's that? Okay, now, let's say I want to compute the integral, the line integral over c of f dot dr, where f of xy is this vector field. Okay, and c is the circle of radius 1 centered at 1, 0, oriented clockwise. Okay, so I'm going to think about my curve. Okay, it's a circle, it's centered at 1, 0, and it has a radius of 1, so it goes right through the origin. And it is oriented which way? Clockwise. So is this positively oriented?
No.
No.
Okay, so C is not positively oriented, which means we can't quite apply Green's theorem yet. Okay. But if we do C going backwards, what happens? It is positively oriented, and then we can do Green's theorem.
Backwards as in counterclockwise?
Yes.
Yeah.
Okay, and remember, I know I just threw it at you last time, but this notation just means the curve C, but going
Pause.
backwards. Okay? Jairus, what was your question?
Yeah, I was gonna be like, wait a minute, is it positive, not positively oriented just because when you're going clockwise in the unit circle, it's like negative quadrant?
I mean, that's kind of why we define positively oriented to be counterclockwise. I think of it
Right.
as if you're a little bug walking on your curve, the interior should be to your left. Here, if I'm a little bug walking on this curve, the interior is to my right.
Interior.
The part that's enclosed by C,
Okay.
The inside of the circle?
the inside of the circle.
Well, also, but if you just think about the radians and you're in the negative quadrant going
Yeah.
clockwise, then that's why it's not positively oriented.
Sure.
Okay.
Okay, so now, let's see, this integral, line integral over C dot dr, how does it relate to the line integral over negative C of f dot dr? Because I want to switch, and instead of thinking about C, think about negative C, because that one is positively oriented.
You stick a negative sign out in front?
Yep, just stick a negative sign out in front.
Nice.
Okay, and now I can do everything that I want to with Green's theorem, except there's a negative thing out front, but that's fine. Okay, so let's see, I'm gonna remind you that f dot dr means I have the x component, or the first component of f, which is y squared minus 2y plus 2xy with a dx. And then I add the second component of f, which is x squared plus 3x plus 2xy with a dy. Okay, and now if I'm looking at this, this is the p, and this is the q. Okay, so, let's see, what's partial p, partial y?
Two y minus 2 plus 2x.
Good. And what's partial q partial x?
2x, 3, 2y.
2x plus 3 plus 2y. Okay, Green's theorem says that this line integral, well, I have that negative just hanging out, but it's equal to the double integral over d of, okay, partial q partial x minus partial p partial y. Sorry,
Sorry.
just yell at me. I'm used to it.
Oh no. We're here for you.
Well, it's my own fault. Okay, and now, sometimes I just like to do this work separately. Okay, now I'm gonna plug in what those two derivatives are. Right, so I have negative, the double integral over d of partial q partial x is 2x plus 3 plus 2y. And then I'm subtracting partial p partial y, which is 2y minus 2 plus 2x. And what is really in those parentheses?
Zero. Nope.
5. Because this 2x minus this 2x cancel, right? And this 2y minus this 2y cancel, and 3 minus negative 2 is 5.
Should that always be the case, like with Green's theorem? Like those
No.
variables will cancel? No?
No.
No, okay.
It just does make life quite a lot easier
Yes.
when it does.
Yeah.
Doesn't work out quite so nicely. Okay, and it just does make life quite a lot easier
Yes.
when it does.
Yeah.
Doesn't work out quite so nicely. Okay, and doesn't work out quite so nicely. Okay, and doesn't work out quite so nicely. Okay, and so this is the answer is negative 5 pi. You guys have any questions yet?
Okay, yeah. So what is this little symbol thing, the integral sign? Just, what's that
Oh, the
tell
little
us?
circle?
Yeah.
It's just a reminder that your curve is positively oriented. So like just for kicks, I cannot put the little circle thing here because this C is not positively oriented, but I can put it here because that C is positively oriented. Right? I could also put it here. But then once I switch to a double integral.
And the idea is just that Green's theorem only applies to a positively oriented curve. Okay.
Or is that?
It means it's a closed curve and it's positively oriented.
Or would the answer not be the same whatsoever? Which I think is an impossibility, so I'm under the impression no.
You really truly did not want to think about C going backwards. Either you can't use Green's theorem, or you'd have to rework Green's theorem for a negatively oriented curve. Which would just be switch the order of the subtraction.
Would the answer be 5 pi then, or still negative 5 pi?
Okay,
That'd be
if
negative
the
3.
original question said that the circle is oriented counterclockwise, the answer would be positive 5 pi.
It'd still be negative 5.
No. If the original question, this word was different and said counterclockwise, then I wouldn't throw that negative on. So I'd end up with positive 5 pi. But if you're asking, what if I really truly was hell-bent on working with it going clockwise? then you either parameterize and do it the old-fashioned way, like using the t, or you have to rethink what Green's theorem means in a weird way.
So what does negative 5 pi mean?
You can interpret this as the work that is done by this vector field or force field on a particle as it travels once around this circle in this direction.
So it got slower?
So
Or
a
that's
negative
just the
amount
energy
of
it
work
took to
was
move?
done.
How do you do negative amount of work?
Because it's going.
Yeah, it just, I mean, it's the idea that like it's going backwards.
Time.
And it's
We're going
like directly
backwards.
on the circle going around. Like the work done by the particle's on the circle.
Yes, the work that's done on the particle as the particle goes around the circle.
Okay.
You could think of it, if instead of thinking about this as a force, you think about it as a velocity, like a wind, then it's how much work is the wind doing on you as you walk once around this circle. I don't know if that's better or worse.
So the wind is blowing against you.
Sure, but it might also be blowing on your back and pushing you. Or it might be blowing on your front and pushing you backwards. You know, like slowing you down versus speeding you up.
Right.
Might be pushing you to the side, and then you just have to like correct so you don't go off course.
I'll just accept negative 5 pi.
That's my plan.
Yeah.
Next question.
Next question. We're gonna compute the line integral where C is this curve. The line integral is over C, that's C, and, okay, well, you see the function. Now tell me, which way is this curve C oriented?
It's just a cute guy.
Positive.
Positively, and how did we know that? Because of the little circle doodad. Okay, circle means C is positively oriented, which makes us happy.
We could put eyes on the top of the shape. Oh yeah, that works too.
Oh, that's not what you were imagining.
Because it kind of looks like a smile. Like a, oh, that's great.
I'm gonna put my family crest on it.
Excellent.
What's that
Okay,
even mean?
if C is positively oriented, we can use
Green.
Green's theorem. Okay, so we can use Green's theorem. Okay, and what is the P?
The first part.
The first part, the one in front of the dx, and the q is the part in front of the dy. And if I want to calculate the derivatives, I want partial p, partial what? Good. Okay, what is partial p, partial y?
That's a good question.
Well, let's see. What's a constant here? Everything except the y to the 4 is a constant, right? So the negative x over 2 stays.
Nice.
What's the derivative of y to the 4?
4y.
4y to the 3rd. Okay, and then I'm gonna simplify, let's see, that's negative 2xy to the 3rd. Okay, and what is partial q, partial x? Okay. 2xy to the 3rd. Okay. So, Green's theorem says that our integral, this one, p dx plus q dy, I'm just writing that so I don't have to actually write out the functions again, is equal to the double integral over d of what?
Partial Q, partial X. minus PY.
Partial P, partial Y. Put it up there, no idea. Just pretend I wrote that in a normal fashion, like in a line. Okay, which is the double integral over D of partial Q, partial X is 2xy to the third minus partial P, partial Y is negative 2xy to the third. And what do I get when I combine those?
4x, what is it?
Yep, so double integral over D of 4xy to the third dA. Okay, so here's an example where it didn't end up just integrating the constant. Okay, so here's an example where it didn't end up just integrating the constant. Okay, so here's an example where it didn't end up just integrating the constant. Okay, so here's an example where it didn't end up just integrating the constant. And right,
Top and bottom.
top and bottom is probably better, right? Okay, because there's really 4 sections here, right? There's the left vertical side and the right vertical side. There's the top horizontal side and there's the bottom circle. Yes? Okay. And if I think left and right, toward the top, the left and right are the vertical sides, but toward the bottom, the left and right are parts of the circle. So then I'd have to split it up in 2, and if I can avoid doing that, I want. Okay, so I'm gonna look at this, and I'm gonna think of it as a top and a bottom. So what's the equation of the top? Okay, so I'm gonna look at this, and I'm gonna think of it as a top and a bottom. So what's the equation of the top?
Y equals 1.
Y equals 1, and what's the equation of the bottom?
Square root of x squared plus y squared.
Nope, I can't have a y.
Y equals x squared minus 2.
Okay, what shape is the bottom half?
Parabola.
Pi.
It's a circle.
Oh.
How do I find the equation of a circle?
X squared plus y squared equals r squared.
Okay, x squared plus y squared equals r squared. What is the radius of that circle?
2.
1.
Uh-oh.
1. Okay, and then solve it for y,
That was 2 units.
right? So y squared is 1 minus x squared. So y is plus or minus square root 1 minus x squared. And now tell me, the bottom half of the circle, is it the plus version or the minus version? Minus version. So negative square root 1 minus x squared.
That was the coolest thing.
Okay, so in my double integral,
That was the coolest thing.
okay, so in my double integral, I figured out the top and the bottom, which means the equations I got, the 1 and the minus square root thingy thing, do those go on the inside integral or the outside integral? Inside. Very good. Because the outside has to have numbers. Oh, if those are on the inside, is the inside one the dx or the dy? Yes, I got confused. Sorry. Okay, dy. Inside one the dx or the dy? Yes, I got confused. Sorry. Okay, dy. Xy to the 4th was the favorite answer that I heard, at least my favorite. And then evaluated here. Okay, and then I'm gonna plug in for y. So plugging in 1 for y, I get 1 to the 4th. And then minus, plugging in that square root for y, I get that thing to the 4th. Okay, did I need more space? No, I did not. I'm gonna cheat just so at least the notes I post are easier to read. Okay.
X minus that?
Huh? Yep.
Oh, what are we gonna use?
So -1 to +1, x minus x times. What happens when I raise a negative to the fourth? Positive. What happens if I raise the square root to the fourth? Squared. So 1 minus x squared squared. Okay, now just some algebra, right? X minus x, 1 minus 2x squared plus x to the fourth. That was squaring. And then distribute the negative x. Negative x plus 2x to the third minus x to the fifth. And, okay, at least those first two terms cancel. So 2x to the third minus x to the fifth. And, okay, at least those first two terms cancel. So 2x to the third minus x to the fifth. Now we're good to go with our antiderivative. So 1/2 x to the fourth minus 1/6 x to the sixth. Evaluated from -1 to 1. Is 0. No question about whether that's 0. My question was in my notes, I have a negative sign different than what I have here.
What does that tell us?
With no force. Or yeah, that one.
Right, the net force or the network as, you know, a particle moves around that shaped curve by that force field is 0. Which doesn't mean nothing is happening. It maybe means like sometimes it's getting pushed outside and sometimes it's getting pushed inside, but it all evens out in the end. I forgot to distribute my negative values. I figured out the number.
Nice.
Do you guys have any questions on that one? I'm gonna fix it so I'm not confused. Okay. All right, so now you're like, cool, Mrs. Ander, you've totally convinced me that that's powerful and useful, maybe. But why the heck should we believe that's true? Okay.
Give us the proof.
This isn't gonna be that bad. Look, it's only one page. Okay, so we are gonna prove Green's theorem on a rectangle. Okay, because things work out much nicer on a rectangle. Okay, we're not gonna worry about it the rest of the time. We're not gonna worry about proving it. We're totally gonna use it. Right. This is the point of the semester work.
I had a whole cereal.
I had to find a new semester.
I've had nothing.
This might be the
I've had
only
coffee.
best I've ever had it happen before.
I had Special K with banana.
All right, here we go.
It's so normal. No, I had it after the cereal. Sorry. It's time for Green's theorem. Green's theorem theory.
Yeah.
Thanks, Jarvis.
You're welcome.
Okay, so we're gonna let C be the positive oriented boundary of this rectangle. Meaning, from A to B, from C to D on the y-axis. We have that rectangle. Sorry, that's a little crooked. Okay, and the interior of this rectangle is D. Okay, I am going to now calculate this double integral. Okay, so if I integrate first with respect, okay, so the thing I'm integrating is partial q, partial x minus partial p, partial y. If I integrate with respect to dx first, what bounds go on that integral? A to b. And if I then do dy, what bounds go there? C to d. Okay, so now I have a double integral, and my function, the partial thing minus partial thing, is subtraction, so I can split it into two integrals. Right, so we can integrate from c to d, integrate from a to b, partial q, partial x with respect to x, and then with respect to y, and then subtract the integral from c to d, the integral from a to b of partial p, partial y, dx dy. I'm trying to figure out what I can do. Oh, this is what I did. Hey, look, I have partial q, partial x, and I'm integrating with respect to x.
Oh, it's canceled.
What's the antiderivative? Q, right? So this inside one is q, but evaluated from x equals a to x equals b, right? And then I have to still do the dy. Okay, now what about this one? This one has partial p, partial y, so I kind of want to integrate with respect to y first. But can I just switch the order of these integrals? Yes, because it's a rectangle and these are all numbers. Okay. So I can do integral from a to b, integral from c to d, partial p, partial y, dy, then dx. Okay, and then in the first one is a function of x and y, right? And I'm plugging in b for the x. So if I think this is really q of x comma y, I get q of b comma y, and then subtract, and then I plug in a for the x, q of a comma y. Okay, and then now the inside integral here is going to work the same way as the inside integral here. Right, the antiderivative of partial p, partial y is p, and then I'm plugging in d and c for the y. So I'm going to end up with p of x comma d minus p of x comma c all over dx. Okay, now I have two integrals. I'm just going to split each of those up. So I have the integral from c to d of q of b comma y dy, then minus the integral from c to d of q of a comma y dy. Okay, same idea with the second integral. I have minus the integral from a to b of p of x comma d dx. And then, because I have one negative here and one negative here, the last integral ends up being added. So plus the integral from a to b of p of x c d x.
Space.
change our viewpoint, okay? So we got something for the double integral side of green sphere. Now we're gonna look at the contour integral, the line integral side. All right. Okay, so C is the positively oriented rectangle. Okay, which means it's going around counterclockwise, right, that way. And there are really 4 parts, right, because there's 4 sides on the rectangle. So I'm gonna call those parts, let's see, I'm gonna start at the bottom left. C1, C2, C3, and C4. Okay? And I'm going to parameterize each of those parts. Okay? So to parameterize C1, X is going to be my variable t, and y is going to be the constant c, because the y value there doesn't change. And t is going to go from a to b. Does that make sense? Keep the y value at c, so you're here, but then let t move from a to b. Okay, then I'm going to do C2. Okay, C2, the x value is always b, and the y value changes. So x is b, y is t, and here t goes from c to d. Sorry. Okay, what am I going to do about C3? Well, the x is changing, the y is not. The y on C3, the top half of top edge of the rectangle is d. If I want t to go from a to b, I go from b to a. Just thinking ahead, I want my inputs from negative t would go from negative b to negative a.
Negative x equals something.
But I don't want, like, okay, the way I drew it, a and b are positive, right? Only in my picture, it wouldn't have to be. But I don't want to suddenly let t be between a positive number and say x is negative, right? Because I don't want x to be negative. I just want it to go backwards.
Negative T? Don't work.
So how about b minus t? How about b minus t? Okay, let's think about it. If, no, that doesn't work, does it? Shouldn't be that hard.
B minus A.
Okay, if t is a, I want x to be b. Ooh, so how about, I feel like I'm making this harder than it should be. A plus b minus t. T is a, this is b. And if t is b, this is a. That works, right? Sorry, that wasn't supposed to be that hard. Okay, and then we're gonna do the same thing for C4. Okay, here x is the constant a, and y is the tricky one. Y has to go from c to d but backwards. So let's do c plus d minus t. I can integrate over C1, right? So C1, we'll do one of these in depth, okay? Q dy. Okay, I can parameterize. So T is gonna go from A to B. I have P and E. I'm gonna plug in T for the X and C for the Y, because that's what my parameterizations say is equal to X and Y. And then dx is the derivative of this, so dt. And then I can do the q and the dy. Okay, so I have q of, well, the x is t and the y is c. And what is dy? 0, because the y is a constant c. Okay, so the point is that entire thing is really just 0. Okay, and so this, okay, that whole thing is 0. This, because I was thinking of it as a parameter, I would have the variable t instead of the variable x, but we know we can just switch variables. Right, so this is the same as the integral from a to b of p of x comma c dx. Like literally just changing the t into an x.
Because x equals t.
Not specifically, no. This is just saying if I have a function of t with a dt, I can use a different letter. And I want to use the letter x because that's what I used in the first half. So this matches this one. Right? So this guy matches this guy.
Oh, because the derivative of y, no, up here we got y.
Okay, what happens if I integrate over
Because q is
C2?
the y part, you know, and the derivative of y
PDX
is
plus
constant, it's just
QDY.
0.
Which is gonna be 0, the dx or the dy? The dx is gonna be 0 on C2, because x is a constant. So this is 0. So integrating over C2 means t goes from c to d. I'm gonna have q of d comma t, because that's x and y, and then dt. And what does this equal?
C and D, Q.
Does it equal the first, second, or third integral in red?
First.
First,
Again, I just have the letter T here and I have the letter Y there, but we know that that doesn't matter. Okay, what about the line integral over C3 of P dx plus Q dy? Which one's gonna be 0, the dx or the dy? The dy, because y is a constant. Okay, and I'm gonna integrate from A up to B of P of x is A plus B minus T, and y is D. And what is dx?
-1,
Say it again, Erica.
-1.
-1 dt. So -1 dt. Because the derivative of negative t is -1. So we have negative, that's this negative, the integral from a to b of p of a plus b minus t comma d.
here.
I'm panicking.
Why is this the same as that?
X equals all of that.
Yeah.
Oh, because all of that equals x.
Yeah.
Well, but that's a dt and that's a dx.
You said negative 1 equals?
X equals t though.
No, x equals a plus b minus t.
Oh, for that one, yeah.
dx equals negative dt.
Then we're still missing a minus.
We're still missing a minus sign.
You took it out.
It's in front of the integral.
So, okay, panicking.
Everything's gonna work out. It's gonna be okay.
You think so?
Yeah. Well, I don't know about
That
the
sounds like
problem.
something
Just,
I
you know.
Oh, okay. So what I'm thinking is almost like a u sub, except it's an x substitution, right? So like x equals a plus b minus t. So dx equals negative dt. So negative dx equals dt. Oh, no. It's all gonna work out. Just like Jared said.
Yep.
Okay, because now this guy, I have this negative. I have the integral. I have p of a plus b minus t is x. And d is d. And dt is negative dx. And I have to change the bounds. Right? So the lower bound here is t equals a, and if t equals a, x is a plus b minus t, which is a. You can't see what I'm writing, sorry. Which is b. Right, and then the upper bound is t equals b, which means x is going to be a. So now the bottom is b and the top is a. But if we flip that, we get another negative. So we got negative a to b, p of x d dx. Okay, which is, I don't know, star, which is the third integral in the red. I mostly did that for people who weren't here. Okay, and then I'm gonna skip over the details, but if I do the integral over C4 of pdx plus qdy, we're gonna get negative integral from c to d of qay dy. Is that it? Are we done? You tell me.
You start again?
No,
Let's just
I'm
read
not
it.
starting
Read
again.
it all then.
What did we say?
You're on the negative.
And I feel like we've lost the plot, right? We got confused. Okay, we did this double integral. And we got these four terms. Then we did this contour integral, this line integral, over the four sides of the rectangle. And the integral we end up with for each of the four sides is exactly these four terms, just in a different way. So, are those two things the same? Yes, and that's the okay. Okay, so I'm just writing the conclusion. The double integral over d of partial q, partial x minus partial p, partial y, dA is equal to the contour integral of pdx plus qdy. You can't see there. That's just the conclusion of everything we just proved.
Look at this green guy over a while, sorry.
Probably not.
Yeah, it's good for you.
Okay, the last page here is just to point out that this is not really something totally brand new. Okay, it's just, I just want to point out some similarities of what we've done before in Green's theorem. Okay, so the fundamental theorem of calculus and the fundamental theorem of line integrals in Green's theorem, they say that roughly integrating a derivative thing is the same as thinking about the function on the boundary of the thing you're integrating. Okay? So like this is the fundamental theorem of calculus, right? So inside this integral is a derivative thing, right? And then over here, this is the function on the boundary of the thing I'm integrating over, but the thing I'm integrating over is just the interval from A to B. Right, and I'm not being super specific, right? Integrating a derivative thing means something about what the function is doing on the boundary. So it doesn't really matter what's happening between the A and the B, just at the A and at the B. Okay, and then the fundamental theorem of line integrals that we did on Tuesday says if we do a line integral of the gradient vector of f dot dr, this is kind of like a derivative thing, right? Right, and then over here, this is saying, well, I don't need to know everything about the function. I only need to know the function at the endpoints, at the boundary. Function on the boundary of C. So C being this curve, right? I don't need to know the function everywhere. I only need to know the function at that point. And then Green's theorem says, okay, and then Green's theorem says, okay, if